Well, hello, folks. This is the Apologetics Academy. We run this most Saturdays at 8 p.m. British time, which corresponds to 3 p.m. Eastern time, 2 p.m. Central, 12 noon Pacific. And the idea is that we bring in different scholars, theologians, philosophers, scientists from across the theological and philosophical spectrum to present to us on topics of interest to Christians, especially those topics that pertain to the question of whether or not Christianity is true, which interests all of us. And there's a number of ways you can participate in the discussion today. You can submit a question anonymously if you wish by hitting the Q&A button, which is at the top of your screen. You can also hit the raise hand button, and during the Q&A and discussion period, I'll raise you, you can click raise hand and I'll promote you to be a co-panelist with the speaker, and you have opportunities to go back and forth and dialogue and discuss what has been said. And you can also simply participate in the chat box as well. What we're going to do is we're going to have an hour of presentation by our speaker this evening, and then we'll open up for open floor Q&A and discussion. Our speaker, and if you want to see the list of upcoming webinars that are scheduled in the calendar, you can go to apologetics-academy.org and click on online apologetics training, and you will see the upcoming speaker schedule. So this evening we have with us Phil Harper, who is better known as SkyDive Phil, who is a YouTuber who has interviewed well-known physicists, cosmologists such as Stephen Hawking, Roger Penrose, etc. And he's going to be giving us a critique this evening of the Kalam Cosmological Argument, giving us an atheist perspective on that. So without further ado, I'll turn over to Phil. Great to have you, Phil.
Thank you, Jonathan. Great honor to be on the show. Look forward to our dialogue. So let me start. Actually, I just want to say the first two pictures you see are pictures I took with my telescope just an hour outside of London. So if you're interested in this sort of stuff, it's not that hard. It's not that easy, but it's reachable. Okay, so critique of the Kalam Cosmological Argument. So it's been presented in many different ways. Hang on, I'm just trying to make sure my power does not go off. Hang on. Right, there we go. Got a green light. Okay, so it's been presented in many different ways. I think the most common way it's been presented is that, and I'm sure all of your listeners know this, but just in case there's one that doesn't. So the idea is that everything that begins to exist as a cause, the universe began to exist. Therefore, the universe is a cause, and there's certain moves that are made to persuade us that that cause must be God. Now, I did have a longer section on the origins of this argument, but I'm going to cut all that out and go to sort of modern science and start from there, because I am going to focus on the science here. So really, I think we can talk about Isaac Newton. He was the one, that came up with our laws of celestial mechanics. And he argued that the universe, as a result of his theories, that the universe must be static, eternal, and infinitely large. And that was a view that was very popular for a long time. However, we then run into what's called Olber's paradox. And what Olber's paradox says is that, well, if you have a static universe that's infinitely big and infinitely old, then the light from all those stars is going to reach you, and eventually you will not have a dark sky. But we do have a dark sky. So there are three possible solutions. Either the universe is not infinitely big, or it's not infinitely old, or it's not static. Now, I've often seen people say that Olber's paradox says that the universe can't be infinitely old, but actually that's not true. It can't be all three of those things. Okay, and then, so the views of Newton are held for hundreds of years, and then along comes Einstein with his theory of general relativity that supersedes Newton, and that gives us a dynamical evolution of the universe. It wasn't Einstein that thought that. Originally, it was these guys, Freeman and Lemaitre, who suggested that relativity implied a dynamical universe. It has to be either expanding or contracting, and Lemaitre in particular pushed a expanding universe. And eventually we got confirmation of that, in particular in 1965, with the discovery of the cosmic microwave background. I love the fact that the discovery of the cosmic microwave background has probably the most understated title of a paper ever. It's obviously a very important paper. And the title was a measurement of excess antenna temperature. So yeah. Anyway, so this is the basic picture that we have of the universe. This comes from NASA's WMAP satellite that mapped the cosmic microwave background. And here's the standard picture of cosmology that we have today. So now in 1979, William Lane Craig published his Kalam Cosmological Argument. And what he did was revive certain ancient arguments that go back to Philoponus in the 400s and now Ghazali and people like that. And he revived it with now this notion of Big Bang cosmology. And here's a quote from Craig. He said, "The initial event has come to be known as the Big Bang, this cosmological singularity from which the universe sprang marked the beginning not only of all matter and energy in the universe, but of physical space and time themselves. The Big Bang model thus dramatically and unexpectedly supported the biblical doctrine of creation ex nihilo." So the first question we should ask is, well, hang on, okay, there's a Big Bang, but why should we say that was the beginning? Well, it's associated with these things called singularity theorems. And the initial, this goes back to Lemaitre, but in particular, I think it was more developed by Robert Oppenheimer. And he is, of course, famous for heading the Manhattan Project, which developed the first nuclear bomb. Now, these early singularity theorems by Oppenheimer had a very unrealistic assumption, and that is that the universe is perfectly symmetrical. So it was very easy for people back in the 1940s or 50s to just dismiss this and say, okay, well, maybe the universe isn't perfectly symmetrical. In fact, obviously it isn't, because there are galaxies and things that have mass and so on and so forth. So we know that assumption is wrong. Also, at that time, what people don't realize, a lot of people think that the picture just given by Hubble, that the galaxies are receding, confirmed a Big Bang. But really, there was a serious problem back in those days, because there's something called the Hubble constant, and we've just released a new video about the Hubble constant. There's still problems measuring Hubble constant, but it was thought to be 500 at that time. I won't bore you with the units, but it implied that the universe was only 1.8 billion years old, and that was impossible to take seriously even then. So, of course, eventually, this number got refined, and now we think it's about 14 billion years old. But what was really particularly significant was these things called Penrose-Hawking singularity theorems. This picture here was taken shortly before Hawking died, I'm afraid. Hawking gave a talk at the Clay Mathematics Institute. There's Penrose. And, sorry, not the Clay Mathematics Institute, the Andrew Wiles building at the Oxford Centre for Mathematics. And that's Andrew Wiles on the left. He's the person that proved Fermat's last theorem. So these Hawking-Penrose theorems, they remove the assumption of perfect symmetry. They don't need that. So they're considered far more robust. And at the time, they were considered a proof of the beginning of the universe. However, these theorems, they do have assumptions. It's not like they don't have any assumptions. So these are the assumptions. There's some technical language here, and I'm going to explain what some of this means. So there are 4 key assumptions of the Penrose-Hawking theorems. The first one is called the energy condition. Now, there are various types of energy condition, but what we really need to know is that the gravity is always attractive. That's really what's important in the Penrose-Hawking theorems. However, if we look at this sort of standard picture of cosmology, here again, this is the NASA WMAP picture, we see there's actually 2 periods where gravity is not attractive. So at the far right, we see this bit where it says dark energy accelerated expansion. That dark energy is negative gravity. Similarly, on the far left, you see this thing called inflation. Inflation is a very rapid expansion of the cosmos, and that's also repulsive gravity. So just to give you an idea how fast the universe expands, or is thought to expand during the inflationary era, it doubles, the observable universe will double in size in 10 to the minus 37 seconds, something like that. So that's, what's that? 10 trillionth of a trillionth of a trillionth of a second. So it's pretty fast. And NASA have come and said, yeah, we've detected a key signature of inflation. So it's pretty much a consensus position that inflation did happen in the universe. There are a few notable cosmologists that don't accept inflation, that have some alternatives. I'll come on to that in a moment. But the consensus position is there was an inflationary era. Now, why is this important? Well, first off, if you want to know more about inflation, please watch our film Before the Big Bang 4, and we interview Alan Guth, who's the creator of inflation, and a few other notable cosmologists, and we go over it. Now, notice that this film is called Eternal Inflation in the Multiverse, and that's because inflation is thought to generate a multiverse, and I'll try and explain why. So basically, inflation is, you can think of a patch of space which we call a false vacuum, but all we really need to know about it is that it's inflating very rapidly. And in inflationary theory, this patch of space is very unstable. It decays, and when it decays, it converts all its energy into matter and radiation. And that is actually the Big Bang in inflationary cosmology. So in fact, you'll see a lot of textbooks say inflation happens after the Big Bang, but that's not really right. Inflation really should be thought to happen before the Big Bang. And so the inflationary space decays and creates this pocket universe, but it doesn't all decay at once. It can't really do that. So there's bits of inflating space that haven't decayed yet. And because they're expanding exponentially, they will create more bits that decay. And so the amount of inflating space can never go down. Once it starts, it will never stop, and it will create pocket universe after pocket universe in what's called eternal inflation. Now, you might think, well, this is just a theoretical idea, but in this film that we made, Eternal Inflation, that's our narrator, that's my wife, by the way. We interviewed Georges Eustathio, and Georges Eustathio was the scientist that was chosen by European Space Agency to give the cosmology results for their Planck satellite, and that was a successor to WMAP. NASA launched WMAP, and Planck is about 10 times more accurate than WMAP, and it's probably going to be the last word in cosmic microwave background temperature analysis. And we asked him, can Planck determine if models of inflation that leads to a multiverse are favored? So here's our first video clip, and we'll see what he says. There might be a little bit of jargon at the beginning. Don't worry about that. You'll hear the take-home message in a second. Okay. Oh, it's not playing the video.
By the
here we go. Right. Okay.
The type of inflation, the Planck data say happen strongly favour flat potentials. So a scalar field evolving in a flat potential, and then inflation is eternal. So the Planck data say that inflation is eternal. The simplest models would have an eternally inflating universe.
And Planck favours those models.
Yeah.
So when I hear all the time on TV there's no evidence for a multiverse, what you're telling me seems to imply there is.
Yeah, and if inflation is eternal, then you have a multiverse. And that's why I say that I think this is the most important result from Planck.
Okay, right. So you get the idea. Now, the point about this, so one is that inflation violates the energy condition in the Penrose-Hawking theorem. And if there's a multiverse, now there could still be a beginning to the multiverse. It doesn't follow that if you have a multiverse, there's no beginning. But what I think does follow is that you will not be able to detect by any experiment that beginning. So here's a quote from Alan Guth. He says, however, if eternal, I won't read the whole thing, don't worry. He says, however, if eternal inflation is a valid description of the universe, and I think it is, then I would expect that all such hypotheses about the ultimate beginning of the universe would become totally divorced from any observable consequences. So that's kind of a very important point, because a lot of people will say, observational cosmology confirms there's a beginning. But really, it's more complicated than that. And in fact, the standard picture of inflation, even actually if we're wrong that it leads to a multiverse, inflation would still erase what happened before. There may be a caveat to that. I'll come on to that later. But basically, we would not have any observational evidence of a beginning if there was one. Okay, now I did say that there are a few alternatives to inflation that people have proposed. It is the consensus, but there are a few notable cosmologists that have presented alternatives. So here's a list of them, and many of them we've covered in some of our other films. An important take home is that all of these models, and I don't know of any exception, all have a pre-Big Bang universe in them. So if you think that, okay, inflation maybe didn't happen, well, what's the alternative? Because inflation is needed for certain things, particularly galaxy formation. So if there was no inflation, the Big Bang wouldn't make any galaxies. So you would have to have some alternative way to make galaxies. And Some of these have been proposed, but all of them have a pre-Big Bang era in them. So again, the observations of a Big Bang does not tell you that there was a beginning. So the next assumption of these Penrose-Hawking theorems, the theorems that sort of supposedly prove there was a beginning, is what's called the space-time is a Lorentzian manifold. So what that means, as I understand it in plain English, is that there are 3 space dimensions, 1 time dimension, and that there's matter present in the universe. Now, we interviewed Roger Penrose. We made 2 films with Penrose because the first 2 films we made weren't that great quality, so we decided to redo them. But so here's him talking about the singularity theorems, just recapping what we've said, and also how this assumption is probably wrong, the Lorentzian manifold.
Initially, there were known to be singularities. That's places where things go infinite and the equations go wrong, in both the case of the black hole and the Big Bang. But the assumptions were that you had very, very special conditions. The matter was of a very special kind, and most particularly, it's assumed to be exactly symmetrical. And that's very unrealistic. So the idea was, can you show that these singular situations occur in completely general situations? And that was what we were able to establish, that within the framework of Einstein's general theory of relativity, so you use Einstein's equations and very basic assumptions like the energy is locally never negative or something like that.
That's the energy condition.
And more or less just some normal things you like to assume, then the space-time must somehow come to an end. And either it's at the beginning or it's in a black hole when things just can't be continued. The equations give up, basically. Now, I'm still holding to these theorems because they're theorems, they're good mathematics. The only question is whether the assumptions are necessarily true. And the question...
Okay, so this is the key point. So he's developed a model basically assuming that, in fact, when you get to the Big Bang, the temperatures are too hot, so that you wouldn't have any matter. And if you don't have any matter, you have to switch to a different geometry called conformal geometry. And that would allow you to remove the singularity. And then in fact, he constructs he thinks there's a cyclic model, which is based on that. Well, I won't go into the details again. Watch our film if you want the details of the model. But the bottom line is the assumption of a Lorentzian manifold is replaced with this conformal manifold. And I just give you an idea, what do we mean by conformal? Think of the angles of a triangle. They add up to 180 degrees. Now double the size of the triangle. What do the angles add up to? Still 180 degrees. That's an example of something we call conformally invariant. It doesn't care about scale. And this is very, very important when it comes to cosmology. So here's the next film we made with Penrose and his colleagues. So you'll just see his colleagues here. And that's Maciej Dynasky is at Cambridge, and the next person you'll see is Paweł Norowski is at Warsaw.
And then Penrose and Hawking proved together is that these are very generic evolution behavior of any state of matter. Whatever you start with is likely to collapse to a singularity. But these theorems really assume that you have a matter content of the universe, whereas what's important in the conformal model is that you don't.
The most important object to describe the space-time is space-time interval. It tells you about distances of events in space-time. And now this space-time interval, mathematicians and physicists encode is something which is called metric of the space-time. The metric is determined by 10 functions, which are 10 components of this object, which is called metric.
Singularity of a collapsing star is, we will say, much more messy. All components of the curvature tensor, which measures how curved the space-time is, blow up, are infinite. In the initial singularity, Big Bang singularity, only one component does, and that can be regularized, fixed by changing to a conformal geometry.
So what is singular in Big Bang is only this one function, which is actually a scale. But scale has meaning in Lorentzian geometry, but it doesn't have any meaning in conformal geometry. The singularity at the Big Bang is only singularity of one function, which is actually not relevant at all to describe conformal geometry.
So by allowing yourself to stretch a metric at the point of the Big Bang, you can make it regular.
Okay, so you get the idea. Basically, if you switch to a conformal geometry, you can remove the singularity, and therefore there was it before. Whether it's the cyclic model that Penrose suggests is another question. Okay, so the third assumption that there's no closed time-like curve. So what's a closed time-like curve? So we know that in relativity, space-time can curve. That's what explains gravity. Can it curve back on itself and form a loop? Well, the famous mathematician Kurt Gödel suggested it could. And people that have constructed cosmologies where this does happen. So Richard Gott and Li-Jing Li, again, we've made a film with these guys exploring their model. They claim that in the early universe, the space-time would be so curved, it would curve back on itself. And they had a very provocative title for their paper. It's called, Can the Universe Create Itself? And that would seem to be utterly absurd as long as time is linear. But, you know, if closed time-like curves exist or are possible in the early universe, then this is, they argue, is possible. But I think the most, it's very controversial whether closed time-like curves are even possible. A lot of people think, no, they're not. Some people say, yes, they are. So this is, you know, contentious, shall we say. What's less contentious, when we interviewed Stephen Hawking, I think he really summed up the, I think the consensus view. So let's hear what he had to say. By the way, that guy there is Thomas Hertog, one of his colleagues. So, but anyway, we'll hear from Hawking.
Real lesson of the singularity theorems is therefore that we need to combine the general theory of relativity with quantum theory in order to understand the origin of the universe.
Okay, so, and Einstein said something, I think, pretty much the same sentiment. You basically, I think the consensus view in cosmology is that you cannot trust general relativity when the curvature of the universe gets to very extreme levels, because then quantum physics will become relevant, or is likely to become relevant, and therefore, you know, it's just not valid to continue to use general relativity. So we need a quantum theory of gravity. And right now we don't have a well-tested theory of quantum gravity. We have a number of what we might call candidate theories. So let's see what Alan Guth has to say about this. So this is again from our film on eternal inflation. And I think he sums up the consensus position. And I think after him, you'll hear Georges Eustathio. So let's
happened before or after the Big Bang. And the answer to that is a little hard to give, really, because there's no general agreement, really, about what exactly the word Big Bang means. The phrase was created by Fred Hoyle in a radio program once in the 1940s. And it never really had a scientific definition. Scientists are more likely, actually, to refer to the Big Bang not as the singularity, which we really know nothing about, but rather as the early period of expansion, which we think we know a lot about. And in particular, when scientists use the phrase Big Bang theory, they're really always talking about this early period of expansion, and definitely not the singularity.
I don't think anybody believes the universe started off with the singularity. That just tells us that Einstein's classical theory of general relativity breaks down. So that classical theory of gravity doesn't apply when you get to very high energies. So it's replaced by some quantum theory, consistent quantum theory of gravity. String theory is a candidate for a theory.
Okay, so I think that's the consensus position. You'll find that in textbooks. I mean, you speak to any cosmologist, I'm pretty sure they'll tell you that. However, William Lane Craig has said this doesn't matter. So let's hear from him.
Have pretty strong evidence that the universe is not eternal in the past, but had an absolute beginning a finite time ago. In 2003, Arvin Bord, Alan Guth, and Alexander Vilenkin were able to prove that any universe, which is on average in a state of cosmic expansion throughout its history, cannot be infinite in the past, but must have a past space-time boundary. What makes their proof so powerful is that it holds regardless of the physical description of the very early universe. Because we don't yet have a quantum theory of gravity, we are not able to provide a physical description of the first split second of the early universe. But the Born-Guth-Vilenkin theorem is independent of any such physical description of that moment.
Yeah, I have to say, the idea of a physical theorem that's independent of any physical assumptions, it really bewilders me. But we interviewed Alan Guth and we asked him about the BGB theorem, and this is what he said.
In 2003, I was working with Arvind Borda and Alex Vilenkin to understand what we can learn about how inflation might have started and how far back it could have gone. And in particular, once we realized that inflation could be eternal into the future, it seemed like a very natural question to ask. Could inflation have also been eternal into the past? And what we found was that inflation could not be eternal into the past. What we basically managed to achieve was proving a theorem which says that any expanding region of space-time that has some minimum expansion rate can only go back so far and not infinitely far. So that means that inflation must have had a beginning. It doesn't really say that the universe must have had a beginning, but it says that the universe could not have been expanding forever up until the present time.
So we interviewed by Ashtekar, and in their model they have a bouncing universe, and so that means the universe could be eternal in the past, and that theorem doesn't prevent that. Is that right?
Yeah, that is right. That is right. The bouncing universe can be, well, I'm sorry, a single-shot bouncing universe can be eternal.
Yes.
There's also the Turok-Steinhardt cyclic bouncing universe, and that really cannot be eternal. That really violates our theorem. At least the claims they make about that universe violate our theorem.
Right. Okay. The models like loop quantum cosmology, string gas cosmology, they could violate.
That's right, with a single bounce.
Okay, so I don't know if you heard what I was asking there, but I was asking about models that have a bounce. And they would just violate the BGB theorem because it assumes the universe is always expanding. So if you have a contracting phase before the Big Bang, then there's no proof of a beginning via the BGB theorem. What the BGB theorem really is saying, the way I see it, is that the space-time, or really any singularity theorem tells you, is that the space-time that obeys the condition of the theorem is past incomplete, can't be completed forever into the past. But you could have another space-time here on the left that violates the condition of the theorem. So the question is, though, but do we have any reason to think that there was a big bounce? And we do. Remember that there's a consensus position is that we need a quantum theory of gravity to analyze the Big Bang. Now, people have worked on quantum theories of gravity. There's no consensus of what the right one is yet. It's still an open question. But something very interesting has happened in the last few years. In the last few years, people have applied candidate quantum gravity theories to the Big Bang, and they found something very interesting. So this is one of the first. This was by Veneziano. Again, we interviewed Veneziano. He's the father of string theory. And he says that in string theory, you get a big bounce, as you can see there. Now, the rival theory is loop quantum gravity. And guess what? They also have a bounce. And there's another theory called Ajarva-Lifshitz gravity. I mean, string theory and loop quantum gravity are the two biggies. But Ajarva-Lifshitz gravity has had a fair few papers published about it. And they also see a bounce. There are other quantum gravity theories. The only other one that I know of that's been applied to cosmology, though, because a lot of these theories are still, works in progress, is causal set theory. The causal set theory also seems to have a bounce. So it seems to me that the idea of a bouncing universe is very commonly found in quantum gravity theories. In fact, I think all the big ones, you see bouncing solutions in them. I don't know of any others that don't have that. So it seems to be the leading candidate for what happened. Now, we don't know it's what happened. We don't have any observational evidence that this happened. But it seems to be at least the leading candidate. So therefore, we have good reason, at least, to think that this may have happened. And in fact, if you look at papers on this, so I did a search here. If you look at the bottom panel, there have been 11,100 papers in the 21st century about the bounce. And that's just with them in the title or the abstract. I mean, there's a lot more papers that this search wouldn't capture. And if you look at the 18 years before that, you see there's only 2,000 papers. So there's been a big explosion of interest in this. And that's the reason why, is because quantum gravity theories seem to imply it. And it even made the front cover of Scientific American. So you can see this is a pretty common idea. In fact, it might be possible even to confirm this observation. People are working on this right now. The Loop Quantum Cosmology guys have spent a lot of time working on the potential signatures of the bounce. So that's the key takeaway I want people to understand, that the assumptions of the singularity theorems may not hold, and in fact we do have good reason to think some of them don't hold. Now, just to go back to the BGV theorem, there are some other things to say about this. So Vilenka gives a very good description of the BGV theorem. I won't read the whole thing out here, but you have to just imagine, I'll read a little bit. You have to imagine sort of a space traveler moving in an expanding universe. And the point he makes is, I'll just read from the middle, that the space traveler, imagine he's just zoomed away from Earth at a speed of 100,000 kilometers per hour and is now headed to a distant galaxy about 1 billion light years away. The galaxy is moving away from us at a speed of 20,000 kilometers per second. So when the space traveler catches up with it, the observer there will see him moving at 80,000 kilometers per second. And if the velocity of the space traveler relative to the spectators, that's the people observing him, gets smaller and smaller into the future, then it follows that his velocity should get larger and larger as we follow him into the past. And in the limits, his velocity should get arbitrarily close to the speed of light. So basically, you'll measure his speed as getting faster and faster, going backwards in time, and it can't get faster than the speed of light. Or can it? Well, you remember that one of the alternatives to inflation, so inflation is this period where the space-time expands at this unbelievable rate. And people have proposed, well, maybe there wasn't any inflation. Maybe the speed of light was very much faster in the early universe. And so this is the idea of variable speed of light theory. And that's a proposed alternative to inflation. And in the Java-Lifshitz gravity, that other theory of quantum gravity I mentioned, here's the Wikipedia page. You'll see this bit I've highlighted. Notice that the speed of light goes to infinity at high energies. So if there were a singularity, well, you couldn't use a BGV theorem to prove it because, as I understand it at least, because the speed of light will go up and up and up and up as you were to approach it. There's also a different interpretation of relativity called the Neo-Lorentzian interpretation. It's not very popular with physicists, but it has a few philosophers that are interested in it. And also that also doesn't have a speed of light as a limit. So if any of these are true, then that would be another potential way around the BGV theorem. Now, even within the context of eternal inflation, so we're not going to assume any prior contraction, we're not going to assume any VSL or anything like that. Other scientists have disputed this idea that it proves even a beginning to eternal inflation. So here you can see Leonard Susskind, one of the founders of string theory. He posted a couple of papers saying that he was taking the opposite view to Vilenkin, who has argued that it is a proof of the beginning. Here's Yasunori Nomura. He's the head of theory at Berkeley and a very frequent collaborator of Alan Guth. And he thinks that the multiverse must be static, and so it doesn't have a beginning or an end. Anthony Aguirre, another well-known cosmologist, founder of the Foundational Questions Institute, he makes the same argument. So just to summarize then where we are with the cosmology. So we do know there was a Big Bang. There's to me, some type of Big Bang event definitely happened. There's just no debate about that. But in order to associate with the absolute beginning, you kind of have these singularity theorems. But singularity theorems are not considered realistic descriptions by most cosmologists. So therefore, whilst we have overwhelming evidence there was a Big Bang event, we can't say it's a beginning. Moreover, there's no prospect of any observational confirmation of a beginning, even if there was one. And quantum gravity is expected to be relevant, and it does seem to predict a bounce. Also, the Big Bang was not the beginning. Okay, so that's what I have to say about the cosmology. Do you want to stop there, or shall I go on to the next bit, which is about entropy?
We can see if anyone has any questions, okay, or whether anyone knows enough about the subject to ask an intelligent question. Okay. If anyone wants to raise a question, then simply click raise hand or submit by Q&A, or we'll just move on if not. There's a question from David, so I'll bring up David. David?
Hi.
Reading. You have a question? Are you
I can't
there?
hear anything. Maybe you can submit it on text.
Okay, I don't know what's going on with that. Anyone else before we move on? Okay, I think not for the moment. So if you want to continue.
All right, shall we continue then? Okay.
Wait, there's a hand from John.
Okay.
John. There's a question from Blake that was submitted. Says, eventually I'd be interested in hearing what Craig thinks of 1, conformal cyclic cosmology, 2, Gottlieb's model, and 3, these Benson cosmologies, and how do you respond to Craig?
Okay, so what William Lane Craig has said about the conformal cyclic cosmology model is that it still has a beginning. It's 2 universes coming out from one central origin point. That's how he described it. We gave that description, we quoted it to Sir Roger, and he said that's completely wrong. It isn't that at all. And if you think about it, it cannot be that, because the way the conformal cyclic cosmology model works is that you inherit the state from the previous eon. So if the other eon is not prior, you can't inherit its state. If it's 2 universes going from some central origin point, then you couldn't inherit the prior state. And this is key in conformal cyclic cosmology, because the way this model works, or if you think what's motivating the model in particular, there's a couple of things. One is the conformal rescaling, which we talked about, but there's another thing we haven't talked about, which I will go on to in the next section. It's all about the next section is about entropy. But there's a very big mystery as to why the entropy is so low at the Big Bang. And it's a big puzzle. And what Penrose argues is that in the prior eon, well, one thing that's not controversial about his model, there are things that are controversial and things that aren't, but one thing that isn't is that the entropy of the universe is pretty much tied up in black holes. So what he argues is that black holes destroy information. Now that bit is controversial. There was a pretty strong consensus that they don't, but that consensus has now been tripped up because there was a supposed solution to this information paradox, and unfortunately it's kind of fallen over a bit. Now people are really scratching their heads going, what's going on? So if information is destroyed in a black hole, then what Penrose argues is that then when you get to the next eon, the entropy is gone. The entropy of the prior state is gone because it's evaporated with the black hole. So if Craig is right, then the whole model doesn't make sense. But Craig isn't right. If you watch our films on the CCC, we do discuss this with Penrose and with his collaborators, and every single one of them, we have 4 theoretical cosmologists in the last CCC film that we made, and every single one of them said Craig had misunderstood the CCC model. Now with the Gott and Lee model, Craig had said that the vacuum state associated with the conformal with the closed time-like curve is unstable. That's what I remember of his criticism, and it's fine-tuned. And Gott said, no, that's just not correct. We do discuss this in the film, by the way, that it's not unstable. The vacuum isn't unstable, and it's not fine-tuned. So, you'll have to decide who you want to believe. And then on the bounce, I think Craig has just misunderstood himself, because in his Blackwell Companion, he said, well, there's good reason to think there can't be a bounce because of dark energy. So we know that the universe is accelerating in its expansion, so it's not going to recollapse. So therefore, there couldn't have been a bounce. That's from what I recall of his comments in the Blackwell Companion. And there's 2 things to say about that. One, we don't know that dark energy is a cosmological constant. And if it's not, if it's something that changes, then it could recollapse. However, I think it's likely that it is a cosmological constant. So assuming that it is, so what? I mean, that just means it's not going to recollapse, but that doesn't mean it didn't collapse in the past. You can have an hourglass universe. So you have expansion for infinity that way, and your mirror image going that way. So let's put it this way. I'm not going to become a baby. Does that mean that I was never a baby? Well, no, of course not. You know, so I think that's just poor reasoning there.
Blake further asks, he says, I know that they were concerned with how your question was put to Penrose. Did you see this? And he links to an article, A Reasonable Faith. I'll link it in the chat. I'm not sure if you've seen it or not. Sec. It was a podcast. But I haven't listened to it, so I don't know whether you've listened to it or not.
Listen to what exactly?
So I linked in the chat to a podcast that Blake sent.
I can't see the chat. Let's just.
Oh, okay.
Do I click on this thing that says Q&A?
You'll see it there as well. Yeah.
Let's try it. Is that how old is that? Because I do remember seeing this. If it's about a year or two old, if it's something more recent.
2016.
Oh yeah. No. Since then, we've made a subsequent film with Roger Penrose, and we put Craig's criticism to Penrose and his colleagues, and you can watch the film and see what they say. Now, what they said in that podcast was that there's no sense in which the other eons are prior, because there's no time apparently when you have when you go into the conformal era. So when there's no mass, there's no time. That's the argument, and therefore you can't say the other eon is prior. That's what they said in that podcast, and that's just wrong. I mean, it's just technically wrong. And in fact, all of the cosmologists in that say this. Why is it technically wrong? Because there's another way that you can look at what's called conformal time by what's called light cones. So the path of a photon through space-time, and so there's perfectly meaningful to talk about before the Big Bang in a conformal framework. It's just a different notion of time. It's not like our experience of time, but it doesn't mean there's no before or after, or that these things aren't meaningful. Right. So there's another question here from Blake. Shall I address that?
Sure. Go ahead.
Okay. Do hourglass models require reverse dynamic array of time? Short answer, no, they don't. Some do. Some people have proposed a reversal of the arrow of time at the bounce, but I've interviewed other cosmologists and asked them about this, and they say, no, we don't see a reversal of the arrow of time. There are other things that people have discussed, how the entropy should be treated when you go through the bounce. And that is in my next section. So I won't go into too much detail there because that'll be in the next section. But the bottom line is some models have a reversal of the arrow of time and some don't. Right. So I've had a challenge to the infinite past. This is the next question from David, that it would entail there has to be a time in the past where the present was infinitely far into the future. I've had a challenge from this from a layman that infinity is a number of finite numbers, so there is no actual infinity, but showing this is wrong by rearranging the finite lines such that minus 6543, yeah, blah, blah, blah. If you start -2 and move to the right, you will never get to 0. I'm going to address that a little later on. That isn't really to do with the cosmology. That's more a philosophical argument. So I hope you don't mind, David. I can address that a little later because I do have some thoughts about this argument. So shall I move on to the next section if there's no more questions?
Sure. Go ahead. John did have his hand raised, but he disappeared. So just go ahead.
All right. Okay, let me just try and minimize the Q&A. Hang on, I can't see my cursor. 1 sec. Maybe I can just move on. Sorry, just trying to find the cursor. It's maybe I can just hit escape. I can just hit escape. There we go. Okay, so let's see if we can get back. Okay, right. So entropy. Now, people were asking about entropy in the arrow of time. So another argument used that the universe must have a beginning is the entropy argument. So the idea is, Well, entropy is the amount of sort of usable energy in the universe. And if the past were infinite, well, we would have run out of usable energy. So the past can't be infinite. Right. So there are a number of different responses to this. One is this reversal of the arrow of time that I think was it Blake asked about. And this is called the Janus universe. So if we go think back to that hourglass and the bounce, this is an idea that's been put forward in a number of different proposals. Anthony Aguirre proposed something like this. Recently, Julian Barber at Oxford has done a simulation of particles just interacting in gravity. And he argues that even in a purely thermodynamic equilibrium state, eventually they would pass through a point where they would be in a low entropy state. They would gravitationally clump together. And that would be a low entropy point. And then you would get two futures, if you like, going from this point. So that's why it's called Janus universe, because Janus was a Roman god who looked both to the past and to the future. So here there's an arrow of time reversal, and there's a sort of low entropy state in the middle. Now, is that a universal beginning? We'll come to that in a minute. There's an ambiguity there. In some sense, yes. In some sense, no. Another possibility of what are called baby universes. So this is the idea that space-time can break into pieces, and there can be a mother universe, if you like, where the entropy is always growing. So there's none of these have a violation of the second law, by the way, or at least the authors of these theorems argue that they don't. So they can break up into the mother universe can break up into smaller pieces, and those pieces could have low entropy because the mother universe is still increasing in entropy. A bit like our, solar system. The Earth is low entropy, but that doesn't mean the whole universe isn't increasing in entropy. And so these babies can be born of low entropy. Another one is CCC. That's the Penrose conformal cyclic cosmology. So recall that he deals with the entropy issue by basically saying the black holes destroy information. And if they do that, the entropy goes with them. So if there's a prior universe, as the black holes evaporate, they take the entropy with them. And now we have a dynamical explanation as to why the entropy was low at the Big Bang. And in fact, a lot of these are all dynamical explanations of why the entropy was low at the Big Bang. So when we interviewed the loop quantum gravity guys, and I asked them, does the entropy, does the arrow of time reverse it? They said no. There were two different answers, because we're actually making a new film about that. But one is that the entropy of the collapsing universe is just increasing. It's not going in the opposite direction. It's just increasing. And then when you get to the bounce, it's all trapped on the horizon of this contracting universe. And then during the bounce, the horizon disappears. So the entropy clock, if you like, is sort of reset at the bounce. There's another potential solution which has been advocated by Alan Guth, and he says that in the context of eternal inflation, there just is no maximum entropy. So you can never reach maximum entropy because there's no such thing as maximum entropy. And the last one is some people have suggested that entropy is observer-dependent effect. So it all depends on your, a bit like what's up and down. Yes, we have definite up and down because we're in the presence of a massive body. But move away from that massive body and you don't have a definite up and down. So entropy could be an observer-dependent effect. So these are a number of potential solutions. There are actually others, but these are the ones that I had time to go over. So the bottom line is entropy doesn't necessarily mean the universe was had a beginning. Okay, so I'm just going to play a little clip of Alan Guth and Anthony Aguirre discussing this reversal of the arrow of time idea, because there is some ambiguity about it. So let's see. Oops, what's going on?
Why is the entropy so low at the Big Bang? And Roger Penrose has been talking a lot about this.
Yes.
And his solution is that the universe is eternal, and there's something that puts the entropy into a low state. Now, he obviously has a very different mechanism. But would it be correct to say that you're kind of agreeing with him in that the eternal universe is a solution to the second law problem?
Well, I think we're agreeing with that phrase, right. But no further than that phrase. Right. His notion of eternal is very different from this one, because this one really divides the universe into two halves, where, and it's never cyclic. The universe then gets bigger and bigger this way and bigger that way. Well, his model is cycle after cycle after cycle.
This was recently dubbed, I think, the Janus universe, which is kind of a nice name for it. I think there's two faces to the universe. So in that version of the universe, the theorem is upheld in the sense that the definition of the expanding universe that you had up here doesn't hold down here. So according to that definition, the universe down here is contracting. Is that a universe that is past eternal? You can question that in the sense that you could say that this is t equals 0 and time increases this way and time increases this way. So it still has a beginning at t equals 0. On the other hand, you could say, if here we are at t equals 13.8 billion, say, there are an infinity of times to our past. That's also true. So I think there's a legitimate debate as to whether that model of the universe is past eternal or not. But there are other possibilities too, as to how the universe could be in accord with the Bordet-Guth-Vilenkin theorem, but could, I think, really be past eternal. If you define a past eternal model, you can. It self-consistently works, but you do have an edge to it. If you can ask what's beyond that edge, and it's another copy of the same universe. So
okay, so now Don Page wrote a letter to William Lane Craig about this because it is quite contentious. And Don Page, for those who don't know who he is, he was a former student of Stephen Hawking, now well-known cosmologist in his own right, and he's also an evangelical Christian. So he wrote to Bill Craig after he did his debate with Sean Carroll, and this is what he said. So he's talking about the bounce in these reversing time models. And he says, well, I won't read you the whole thing, but he says, it is erroneous to say that the bounce is a true beginning, since the structure of space-time there has time-like curves going from proper time of minus infinity through the bounce and then proper time to plus infinity. So the way I understand this is that you could try and say the middle is the beginning, so there's still a beginning, but it's a thermodynamic beginning. It's not a geometric beginning. There are no point. I think the really important thing is there's no creation ex nihilo in these models. So there's no point. There's an infinity of time going plus to minus, and there is no point where the universe doesn't exist. There's just a point where it has its low entropy, and that's in the middle. So, and he says here, it's rather artificial to say the universe began at the bounce, since the middle, just because it happens to be where entropy is minimized. I think Sean made this point very well in the debate. So now I want to move on to, well, what if the universe did begin? Because I'm not here trying to say the universe didn't have a beginning. It may have done. I think we don't know. And the supposed proofs of the beginning, I think, don't really prove the beginning. That's my take. But what if it did have a beginning? So I think there's a couple of issues. The first is quantum mechanics and causality. Yeah, that old chestnut. So Alex Vilenkin, is someone very well known for saying that the universe had a beginning. He feels very strongly that it did. And he's quoted a lot by theists in that. But where they don't quote him so often is what he thinks, is the nature of that beginning. And this is a quote from the very same book where he said the universe must have had a beginning. And he says, if there was nothing before the universe popped out, then what could have caused the tunneling? Remarkably, the answer is that no cause is required. In classical physics, causality dictates what happens from one moment to the next. But in quantum mechanics, the behavior of physical objects is inherently unpredictable, and some quantum processes have no cause at all. Now, I know what the response is going to be. I've seen enough of these conversations. And what the usual response from people like William Lane Craig and others is that, well, there are different interpretations of quantum mechanics, and some of them do have causality. So one that Bill Craig stresses a lot is the de Broglie-Bohm interpretation, or pilot wave theory, it's also known as, and that does have causality. So we might ask the question, well, what is this? It's true, I think, that that physicists don't agree on the right interpretation of causality, of quantum mechanics. However, so I think Craig is absolutely right about that. However, what's less appreciated is that the consensus view, as I understand it, is still that there is fundamental randomness, not just apparent randomness, but fundamental acausalness in quantum mechanics. So there have actually been some serious studies on what the opinions are in the physics community on this. And as you can see, now the reason these don't add up to 100, by the way, is that people could vote for more than one thing. But notice that there is a clear consensus that randomness is fundamental in quantum mechanics. There's also been surveys of which is the preferred interpretation. And as you can see, the de Broglie-Born one that Craig pushes has very little support. In fact, these are the only two sort of surveys that I know of that have been done sort of with any reasonable thoroughness. And the next one here, you'll notice that the de Broglie-Born one has 0% support amongst physicists. The Copenhagen is the most popular in both of them. And then sort of, I don't know, it's usually the next most popular. There's this one information-based one, and that also does have a sort of fundamental randomness in it. And then the next one is the many worlds one. And there's a question of interpretation of whether that one does or not. Some people say no, it's fully deterministic, but there's some ambiguity about that. But the point is, yeah, we don't agree as to which is the right interpretation. But I think as long as causal interpretations are at least taken seriously, then I think it's at least a candidate for. Then I think what Vilenkin says is a serious candidate for what happened at the Big Bang. And shouldn't be sort of dismissed in the way that it often is. The next thing I want to say is how I think causality is related to time. So we all hear these funny, we know that correlation does not equal causation. So here's a funny, you can look up loads of these hilarious correlations. So there's a 97% correlation between total US highway fatalities and the fresh lemons that are imported to the USA from Mexico. Now, of course, we don't think there's a real causation here. It's just a coincidence. So then how do we determine, well, if two things are highly correlated, how do we determine what the causality is? Well, there's something that's often used in social sciences, in epidemiology, in a number of fields called the Hill criteria. And here they have a look at a number of things, but one of them is, the effect has to occur after the cause. Otherwise, you can't say one thing caused another one. Now, I know people say in these circles, in the Kalam circles, oh, you can have simultaneous causation, but I just don't think that you can. I mean, in classical physics, effect cannot occur before its cause. In the theory of special relativity, you have these things called light cones. This is what I was talking about before with the Penrose things. And causality means that effect cannot occur that is not in the path of the light cone. And actually, in relativity, you can show that there's people can maybe take a screenshot of this and work through the maths themselves. But you could show that if you could send a signal instantaneously, if there was simultaneous causation, you could send a signal backwards in time. And this is beneath here is a little proof of that. So that would actually destroy causality. So I think, and also, the only causes we know of exist in space and time. We don't know of any causes that are not in space and time. So if I ask you to name, the causes of World War II, you're going to say things like the Treaty of Versailles, the rise of fascism in Europe, all these things that happened before. You're not going to mention the Vietnam War, So causes happen before their effects. But of course, if the universe has a beginning, then there is no before. And so I'm just not convinced that you can talk meaningfully about causality. I mean, maybe you can, speculatively, but it's nothing that we know of. The only thing we know of in terms of causality is it exists in the past. The other thing that we know about is to me, it's bound up with the laws of physics. So I can say, if I push a glass over and it falls onto the floor and breaks, that I cause that because I actually know something about the laws of physics. But if the laws of physics didn't exist, then I couldn't say, or if we knew nothing about them, I really couldn't say that me pushing the glass caused it to break. And in fact, this is another letter from Don Page, and he makes this point. And again, he's an evangelical Christian, but he says, we learn our ideas of causation from the lawfulness of nature and from the directionality of the second law of thermodynamics that lead to the common sense view that causes precede effects. So to me, then, if you didn't have laws of physics and you didn't have prior moments of time, I just don't see how you can confidently talk about a need for causality. There's one last thing, is that there is one school of philosophy associated with Bertrand Russell called eliminativism, which basically denies that there is any causality. I mean, they basically say, well, there's just patterns, that things follow patterns of the laws of physics. And Russell said, the motion of mutually gravitating bodies, there is nothing that we call a cause, nothing that we call an effect. There's just merely a formula. Now, I'm not saying they're right, But I think if you can see that this notion of causality existing, you know, without space and time, without laws of physics, it is more dodgy than it would appear at first sight. I think when you just think of your intuitions, oh, well, everything has a cause. Yeah, intuitively that seems to be right. But it turns out that it's just not so simple. Okay, so I'll stop there about causality and entropy. And the last thing I'll have to say is about infinity. But do we want to stop there and discuss that, or go straight to the infinity?
And then wrap up if you like, and then do the last part of your talk. Let's see, Vladimir Susik submitted a question. When you speak of time, it seems that in different theories, time can take different definitions. Would a fair universal definition be an arbitrary measurement of difference of movement of existing matter and or fields in space?
So if I understand the question, there isn't, I think what they're trying to say is there like a universal now? And different observers do not agree on the passage of time. So if you move very rapidly, or if you're in, then your time will be seen to slow down by other observers. If you're close to a strong gravitational field, your time will seem to slow down. There isn't a universal notion of now in physics as I understand it.
We have a hand raised from Mentalist, so I've put him in the panel. Hello, Mentalist.
Oh, hi, Jonathan. I don't know if you can hear me. I assume you can.
We can hear you. Yeah, go ahead.
You can. Sorry, I was only, I've not used this before, so I was trying to type a question. All it was for something later on. I've lost the question, so I'll just try and ask Phil what it was. I chatted to Phil before. I'm not up on the cosmology like he is, but when I chatted to Phil a few years ago, the one question I would want to ask someone like Phil or any cosmologist is, and I'd be interested in his own personal views. If we assume that, well, not if we assume, let's not assume, does he believe, first of all, that something cannot come from literally, I'm using the word specifically, they're literally nothing as a metaphysical principle? The caveat being that if we believe that, therefore we're left with thinking about the nature of that which has always existed. So if we're thinking about, so I know I'm getting more philosophical than cosmological here.
Yeah, that's fine. That's fine.
If we're thinking about the nature of that which has always existed, do you think, Phil, I'd like to know what you personally think, do you think then, from all of your studies, that the nature of that which has always existed bears the properties and nature of intelligence, or just bears the properties of brute matter, physical laws, energy, and function and behavior alone?
Okay, let me try and take that. So a couple of bits to that question. So the first bit was, can something come from nothing? And absolutely nothing, as it were. To me, my own opinion on that is that we've never seen nothing. There is nowhere in the universe that we can look to find the absolute nothingness that philosophers talk about. So we don't know if that sort of nothingness is really even ever possible.
Nothingness is the complete absence of anything.
Yes, I understand how you're defining it.
So,
I'm familiar with that definition.
So
but what I'm saying is we've never observed that. We don't know if anything, let's suppose you could have some, it's hard to describe, isn't it? Because you have to try and picture some.
Yeah, it's actually incoherent. As you're
well,
there.
Some people say it's incoherent. You can never concept. I don't know. Maybe you can, maybe you can't. I mean, I think we just don't know. There's another thing about this notion of absolute nothingness. See, a lot of people, and this is just my own speculation, okay? This is not anything concrete. Why can't things come into, so when we think of the closest we can get to nothing is like a vacuum, okay? And things don't pop out of a vacuum spontaneously other than sort of quantum vacuum fluctuations. They do fluctuate from a vacuum. Now, but there's a reason why, tables and chairs don't come out of the vacuum, and that's because we have a conservation of energy law. Now, if you have true nothing, there wouldn't be any laws either. So you might argue maybe something could happen because there's no laws to prevent them happening, right? Because there's literally nothing. So there's no laws. So what would happen when there's no laws? I don't know. I don't think anyone knows what would happen when we know what happens when there's laws, right? When there's no laws, when there's what's to stop something from happening? I don't know. I mean, I think it's very speculative, and I don't think we should make firm statements about this. I think no one knows. Now, there is a model, just before we get to your thing. Well, I guess this is related to your thing. There is a model that I think is the closest to a universe from nothing. And I think it's been misunderstood. Because when I hear theologians talk about, we hear a lot of physicists say, we can have a universe from nothing. And they say, no, that's not nothing. That's the quantum vacuum. And the quantum vacuum isn't nothing. And I think these critics, and they're not just theologians, actually, there are some other non-theologians that have made this criticism. I think they've misunderstood it, because the model that I would think is the closest to this is what's called the Vilenkin tunneling from nothing model. So it's Alex Vilenkin's model.
Yeah.
What he suggests is that if we treat space and time quantum mechanically, then space and time can fluctuate into existence. So from a state where there is no space and time, there's no space or time, and yet space and time can spontaneously fluctuate into existence. And this is, I think, as close as you can get to a universe from nothing, because there really are no things. It's not from a vacuum.
No.
The vacuum is what populates space, but this is not that. Now, is his model right? I have no idea. We don't know. It's a speculative model. Okay. Now that's the one that's close, but there would still be laws of physics. They would have to have some sort of
precisely
ontological existence. So that comes to your question: that in that sense, you could maybe argue that's the uncaused cause. So then would they have to have intelligence? Well, this is now a sort of very difficult question. How do you treat the laws? A lot of people say laws are just descriptions of events. They don't have their own existence. Some physicists say no, they do have their own existence. They're more than just descriptions. And if that's true, then maybe Vilenkin's model could be realized. I have no idea if this is right, and I don't think anyone knows if it's right. But that would be the closest to that sort of scenario.
Wouldn't it be the case so that when we're talking about, and I agree, Vilenkin's is most starkly something from nothing, if there is such a thing, it's still the case, isn't it, when we're talking about trying to identify behaviors, potentialities, things that we're observing, happenstances, I'm making words up now.
Yes.
None of those, even when we do science and cosmology, you're observing and trying to understand. To me, it's a little bit analogous to things like dark energy and dark matter. Now, we know more about them than we used to. We still don't know how they operate and the complexities and how they function. You will know a lot more about these things than me. We're not talking about incoherent principles of something coming from nothing. Even Vilenkin's models are talking about something that's so difficult to understand. But
it is difficult to understand, and it might not be right, but it's a perfectly consistent model as far as I understand. And it might be right. I mean, we don't know that it's right. It's one of many proposals for the early universe. And so
what I think is to try and put it simply, I think what we're talking about, what Vilenkin or others talking about, are things coming from things we know nothing about and have no idea what they are.
Well, I don't. Yeah, I would disagree. I mean, what he's saying
he's not.
If we can apply, if we can say we know the laws of physics, so it's not like he's just pulling this model out of a hat. It is. Do the laws of physics allow this? And what he's saying is yes, they do. Now, of course, that brings you to a difficult question. In what sense do the laws of physics exist when the universe doesn't? That's a very problematic notion. And that could be a fatal problem for his model, but maybe not. That's something we don't. So in that sense, I agree. We know nothing about what it would mean to have laws when there's no universe. But it's not true to say that we know nothing about the laws. I mean, we know what the equations are. And what he argues is
relative to what we might expect to know in 100 years.
Well, yeah, of course. I mean, so as we develop theories of quantum gravity, we'll see if this is even allowed. And there is some debate as to whether this is allowed. I mean, a lot of people in the quantum gravity theory would say you can't have an infinite density, at least. That when you go back in time, you'll get a bounce. You won't get this tunneling from nothing. But this is still contentious. We'll see. Just 1 second, mentalist. There are a couple of other questions. So I just want to say to those other people, Anonymous, Blake, and Leif, we're not going to ignore those. But you want to say one other thing, mentalist, and maybe we should.
Yeah. Sorry, Phil. All it was, rather than being preoccupied with that first thing, was just really on the second. So even if we get to a point of thinking something can come from literally nothing, or therefore something has always existed.
Yes.
Really, my interest is what's the nature, what's the actual foundational nature of that which either began or that which has always existed, and then to think, or then to ask, do we say it's just brute nature, matter, energy?
Well, I think there's two options. There's two options to me. Well, three actually. You could take a theist position and say there's some intelligence. You could take a position and say it's just a brute fact. There's no further. You just bottom out when you get to an explanation. In a similar way as particle physicists might say, well, look, like everything we know of is made out of something smaller, right? You know, I'm sitting on bed here, and it's made out of atoms, and they're made out of protons and neutrons, and they're made out of quarks, and are the quarks made out of strings or some other fundamental? But eventually, I think it bottoms out, right? So maybe the chain of explanations bottoms out as well. The other third possibility is maybe there's something that's just necessarily true, and it might not be God. It could be maybe the laws of physics just have to be the way they are.
Would you agree it bears the hallmarks of intelligence, though? That's really my question.
It depends. I don't think it implies an intelligent being behind them. No, not necessarily. It could be. I mean, I'm not saying it cannot be, but I don't think that that's something that has to be true. I mean, it's just a speculation. It could be, and then of course you would ask, well, where does the intelligence come from? So of course that'll get us into necessary being stuff. Separate debate, But yeah, okay. So can I answer some of these other questions?
Sure. So
we can come back, mentalist, if there's time. Okay. So all right. So let's talk Blake. He says, what about a chandelier chain causing a chandelier to be in a given location? To me, that is not simultaneous causation, because the force that's holding up the chandelier, there's gravity and there's electrostatic forces. They appear to be simultaneous and can't. The famous example, of course, is Kant with his ball on the pillow, and he says, well, it's simultaneous, and they appear to be simultaneous just because the speed of light is so fast. And these forces, these in physics, these things are transmitted by forces that travel at the speed of light. And so they appear to be simultaneous, but they're not simultaneous. So if the sun were to disappear, in Newton's theory of gravity, which is what Kant understood, yes, we would feel it instantaneously. But in relativity, we say no. The sun is 8 light minutes away, and nothing would happen if the sun disappeared for us for 8 minutes. So similarly, the ball sitting on a pillow, okay, the speed of light is really fast. It seems to be simultaneous, but it isn't. Same with the chandelier and all these other examples. All right, so what's the next one? You seem to create true randomness and non-causality. If I did not misunderstand this, how do you justify this, which for me seems to be a leap? Also, there seems to be a genuine impossibility to actually confirm genuine randomness, since there could always simply be a more complex pattern generating what seems to be random. Okay, so my understanding is that there are ways to test for true randomness. It's not something I'm particularly well versed in, but there are ways to do that. And so far, the quantum mechanical processes pass those tests. Now, that doesn't mean there cannot be something else, but the space, there's sort of a space for where the sort of non-randomness might hide is getting very, very small. And it could be that people are developing experiments. There are models of quantum mechanics that have true randomness, that make predictions that you could tell that interpretation is different to that one, and they do. There are ways to test these things, as I understand it. So now, so to me, it is not impossible to tell which is which. So now, am I equating true randomness to non-causality? I mean, well, yes, I am, because if event A happens and then event B happens, if it's purely random, whether it's a B, let's say event A happens and then event B or C happens, Okay, and if it's purely random whether B or C happens, then there's some, it's not purely causal. Now, I'm not especially well versed in interpretations of quantum mechanics, so I can't, and the films that we have done haven't really covered this, so I can't say that I can speak for anyone here. But that is my understanding. And that's why I think Craig rightly points out that there are these other interpretations and appeals to those. He doesn't say, well, on all of the interpretations, there's no breakdown of causality. That's not what he says. He says, we've got these other interpretations like the de Broglie-Bohm interpretation. And so he's right to appeal to those. And therefore, yeah, so I think there is an equivalence there. Right, so what's the next one? Anonymous says, just wanted to let you know that Russell rejected the idea that physics has undermined causation and later argued causation was something science had to presuppose. I mean, I don't know about that. I've not heard that. It may be true, but that doesn't mean that he's right. You know, if he had one view here and another view there and he changed his mind, that doesn't, you know, we're not saying it's true because Russell says it's true. You know, it's a view that some people take. Sean Carroll took that view in his debate with William Lane Craig. It's a definite school in philosophy of physics. And if they're right, then the Kalam is going to be in trouble. Okay, right. So Blake has said something else, right? Interesting point. Thanks. Follow up. If you have time, I wonder if there could be a sort of alternative physics wherein we could see a chandelier situation. And if so, simultaneous causation would be possible. And this is relevant because we're talking about philosophical possibility rather than natural possibility. I mean, I guess, yes, of course, you could always entertain some alternative physics. Sure, of course you can. But then, you know, you have to justify that. And also, you know, if you're trying to argue that the Kalam is backed by modern physics, and yet you're going to appeal to some alternative physics, then I think you'll be contradicting yourselves. So it's fine if you argue for the Kalam based on purely philosophical notions, but if you're going to say modern physics backs it, and then you're going to have to presuppose some alternative physics to get you your simultaneous causation, then I think you'll be contradicting yourself. Okay, so Blake says something again. If there was a gunky, non-discrete, non-particle chain chandelier situation, I'm not quite sure what you mean by that, Blake. Do you want to elaborate? A gunky, non-discrete. Well, one thing I would want to say is if you want to say things are not discrete, then you're going to have a problem with infinities, as we'll come on to in a minute, because if things aren't discrete, then you can cut them up indefinitely. Then you're going to have an actual infinity. And I thought that the Kalamist doesn't like actual infinity. So I feel you need to have discreteness in order to avoid infinities. So, okay, right. Okay, so if there's no more questions, are there any more questions? I'll go on to the next section.
I think.
Okay, right. Okay, let me escape. All right, so basically, okay, let's get back on here. All right, so basically the last bit is about the actual infinite. And I have had discussions about this with these physicists I've interviewed. And so these are my thoughts on this. Some of it's from those discussions, some of it's my own thoughts. And I'm not an expert on these things. I interview the experts. So these are my own thoughts. So first off, people say, well, you can't have an actual infinity. However, to me, there's a contradiction here because the people that advocate the Kalam, like Craig and others, appeal to singularities, but singularities have infinite density, infinite curvature, infinite pressure, and infinite temperature. So if you can't have infinities, how can there be singularities? So that's problem number one. Problem number two is that infinity is perfectly well defined in mathematics. There's a broad consensus in mathematics that infinity does not involve logical contradictions, that it's perfectly well defined. Now, the people point out supposed logical contradictions with the infinite, and that is because they're treating, in my opinion, and the people that I've spoken to, they're treating the infinite as a finite number. And infinity is not like the largest finite number. It just doesn't behave that way. Infinite sets have different properties to finite sets. And if you treat them as finite sets, yes, you'll run into crazy stuff, but they are not finite sets. So in fact, actually, I just want to say one thing. It's just a little bit interesting thing about the history of this is that the Hilbert Hotel, which is often appealed to, was actually, Hilbert did, I think, initially write about it. I don't think he ever published it. It was actually a physicist called George Gamow who pushed the idea of a Hilbert Hotel. And he was trying to show that the Big Bang Theory made logical sense, because back in those days it was still being debated. He said, look, you can accommodate more guests in an infinite hotel because infinite sets behave differently to finite sets. And he was trying to argue that if the universe was infinitely big, it can still expand. And he appealed to the Hilbert Hotel to try and do this. So there's sort of irony that people are using the Hilbert Hotel to try and prove the beginning of the universe. But it was actually Gamow that actually was the one that really pushed the Hilbert Hotel to try and argue that the universe could be infinite. Okay, another problem is that in Christianity, as I understand it, you have an eternal future. We're promised eternal life. And at the Biola University, I've read their thing they have to sign, and they have to believe in eternal punishment. So there is an eternal amount of time in Christianity. Now, some people say it's a potential infinite. It's not an actual infinite. To me, if God can see the future, then it's no longer potential. So I could ask God, I'm going to go to hell because I don't believe in you. So how many screams will I scream in hell? And God can tell me it's an infinite number, right? Because he can see the future. So I would agree maybe it's a potential infinite unless there's an omniscient being that can see the future, in which case to me it's actualized. Okay, so there's also, there just is no notion of now in relativity. So it's not like the universe has to get to now. There's this sort of issue of how could the universe transverse this infinite period of time? But it's not on a journey going, you know, from the infinite past to now. There just isn't a notion of a universal now in relativity. Now, we actually asked Roger Penrose this very question: how could you transverse an infinite amount of time? And you should watch our first film on this, because he talks about this. He says, well, in conformal time you can, because to a photon which experiences conformal time, 1 second, million years, trillion years, it's all the same. There's no difference. So it's a bit like, you know, the old solution to Zeno's paradox. You know, well, if you can move infinitely, you know, if you can move infinitely quickly, you can go to an infinite distance. So it's something maybe analogous to that. And the other thing is that there just is no starting point. You know, we talked with another physicist. This is an upcoming film, and you know, we mentioned this. And we talk about an analogy of a race, where okay, you start the race when you shoot the gun. But what if I say you wait till you count to infinity and then you shoot to the gun? Of course, you're not going to ever shoot the gun, right? You're not going to start the race. But that's because in this scenario, there's a starting point. But in these models of the universe, there just is no starting point. So it's not like you have to wait from there to here, because there isn't any there to go from. The other thing is this view that you can't transverse the infinite. So it does depend on what's called an A theory of time, because as we said above, there is no notion of now in relativity, and the way it's generally understood. Now, there is an alternative interpretation of relativity called the Neo-Lorentzian interpretation, and that would have a sort of now that you would have to get to. And now I'll come back to that in a moment, just to try and give you the idea that cosmologists certainly do not rule out infinity a priori, because there's some logical incoherence with it. This is NASA's WMAP website, and they talk about, is the universe finite or infinite, and they're perfectly happy to say it may be infinite. Most cosmologists say we don't know. Oh, by the way, some people have said that the singularities are potential infinites. And here's John Barrow, who is also a Christian, by the way, and he says no, these would be actual infinites, these singularities. And why? Because if it were potential infinite, you'd never get to it. So you could extend the universe into the past indefinitely, because you're never actually going to get to the singularity. But the whole point about singularity theorems is that you get to an infinite curvature, density, pressure in a finite amount of time. And that makes them actual infinites. So again, is the universe spatially infinite or not? This is a very popular blog. And again, notice that they're perfectly happy. I'm just going to talk about is the universe spatially infinite. So try to put us on a bit more neutral ground. And notice that they say, no, happy to say it's either finite or infinite. We don't know. The European Space Agency had the same question on their website. They interviewed Joseph Silk. And notice the question here is the universe finite or infinite. It says we don't know. John Barrow also said maybe we will never know. Alex Valenkin thinks that it actually is infinite. So you can get the idea here. You know, cosmologists, mathematical physicists do not think that the infinite is disallowed. You know, now coming back to this interpretation of neo-Lorentzian interpretation of relativity. So this is Craig at the bottom here, and he does say Kalam is based on the A theory and this neo-Lorentzian interpretation. Now, if you go to the top panel here, there was. Does anyone remember? Well, you're all muted, so you can't answer. But you might remember a few years ago, it was thought that they had been discovered faster than light neutrinos. And when this was first reported, William Lane Craig put out a post saying, well, look, this is not surprising on the neo-Lorentzian view. So here's his passage, and I'll read you a little bit of it. He says, Lorenz was right all along. If there do exist relations of absolute simultaneity, and Blake, that's probably the alternative physics I think you're probably thinking of, then there's just no problem with faster than light signals. Indeed, if we had infinite velocity tachyons, we could use them to measure absolute simultaneity. So that is what you would need for this absolute simultaneity. So the reason for that panic you sense in the press releases on the CERN results, so that this is the faster than light tachyons, is that the scientists interviewed implicitly assumed either an Einsteinian or a Minkowskian interpretation of special theory of relativity, but Lorentz would be rejoicing. So, okay, yes, if you had faster than light signals, then you could entertain this neo-Lorentzian view. The neo-Lorentzian view does have faster than light signals, but recall that the BGV theorem assumes that you cannot go faster than light. So I think there's a contradiction here. And I think the Kalamists need to choose what they want to use, because they're using the BGV theorem, well, it implicitly assumes that you can't go faster than light. But if you're using the neo-Lorentzian interpretation of relativity, well, as Craig points out, you can go faster than light. So to me, you need to choose what you want to use. Okay, so right, this is, I won't stop here. This is going to be my last section where I play in a video, and we're almost to the end here. So the last bit I want to talk about is just about Genesis and the Big Bang. So here's Jeff Swearing, who I did a show with on Unbelievable. You should listen to that. It's on my YouTube channel, and I'm sure you can just Google Jeff Swearing, SkyDive Phil, and you'll find it. But this is Jeff and Reasons to Believe, and they argue very strongly that Genesis is talking about the Big Bang. Oops, not playing.
It's important to look at that this isn't God or that the Bible saying that God created the heavens and then God created the earth. It's actually God created the heavens and the earth. It's a compound biblical word or Hebrew word, if you will. So it would be in modern terms, we would say in the beginning God created the universe. And so as we look at what does it mean for God to create, we look at that word create, and it's actually the Hebrew word bara. And when you look at what does that Hebrew word bara mean, it has a couple of very interesting connotations. First, it's a word only used of divine activity. So this is God, the maker of the heavens and the earth, God the creator, who is at work doing this. That is his direct work that brings the universe into existence. And when we look at the word for created, we also get that it is God bringing into existence something completely new, something that did not exist before. And this is where Christians get the doctrine of creation ex nihilo, creation out of nothing. God didn't refashion some pre-existing stuff. God brought the universe, something completely new, into existence.
Okay, so now I went to Hebrew school, and I remember discussing this with my rabbis. This beginning text in Genesis 1:1, I just don't agree with this interpretation. And it's not just me. I mean, I'm no Hebrew scholar, but and I barely remember my Hebrew, if I'm honest. But I do remember some of these words because some of them are quite important in Judaism. But what's important, you can look up what the Jews think about Genesis 1:1, and different rabbinical schools debated whether there was creation ex nihilo or not. A lot of them said, no, God created out of pre-existing materials. So if the Hebrew obviously said this, and then there should be a consensus amongst the rabbis, and there definitely isn't. In particular, the word Shemayim, to me, it means the sky. We talk about it means the heavens, but you can look at this as strong concordance. So this is not my view. This is Strong's Concordance, and they say it can mean sky. And in fact, the birds fly in the Shemayim. Eretz, every Jew knows the word Eretz because we're always singing about Eretz Israel, the land of Israel. Eretz means land. So yes, it was translated as heavens and the earth. And to us, modern people, we think of that as, you know, the universe, space, and then the planet Earth. But no, to the people back then, it meant you could just better be translated as God created the land and the sky. And Baruch, again, in Strong's Concordance, doesn't say anything about creation out of nothing. It means to shape or create. And the reason, and it says fashioned by cutting, you know, but because I think they had this view of a solid dome, like a dish, and they were beating out the dish. And that's where the Baruch, and in fact, of course, we don't think Adam and Eve in Genesis came from nothing. And you can see right here, Baruch. So I just don't agree that it means that. So just to sum up, and then I'll be finished with my presentation. There are some hidden assumptions, I think, in the Kalam. It looks like there's just two assumptions, right? But there aren't really, because all these things, I think, would seriously undermine the Kalam. So you have to assume an A theory of time. Well, actually, I'm not sure you have to assume an A theory of time. I think you have to assume an A theory of time for the philosophical argument. So if you're using that, then you need an A theory of time. You have to assume that there can be simultaneous causation, because if that's not the case, and I think modern physics would probably say that is not the case. I mean, there can be some ambiguity about these things, but if that's not the case, then if causes precede their effects, then the Kalam is going to fall apart, because it doesn't make sense to talk about cause before the universe. You also have to assume minds can exist without brains. And a lot of people that defend the Kalam say, oh, modern science has shown us there was a beginning. I don't think that's true. But I also think you speak to neuroscientists and philosophers of mind, I think you'll get the view that minds can't exist without brains. And of course, there's a controversial assumption there that they can. And so there is, more controversial assumptions than are at the eye. Also, you have to have agent causation without pre-existing materials, without energy consumption or a prior moment of time. Now, when I see agents causing things, our experience tells us they use pre-existing materials. Agents never cause things without using pre-existing materials. They never cause things without just consuming energy. They never cause things without there being a prior moment of time. So you've got to assume that there was agent causation without any of the things that we normally associate with agent causation. Now, maybe there could be. I'm not saying there cannot be, but clearly, it's not something we just know to be the case from our experience. You also have to assume there's a meaningful distinction between efficient cause and material cause. So Aristotle made these distinctions because, and the example like John Lennox gives is, what's the cause of the kettle boiling? And he talks about, you can talk about the atoms moving around, but really it's I want a cup of tea, but he's assuming that I want a cup of tea is not material, right? So, but I think a lot of people would say, no, you're wanting a cup of tea is material, and your wants and, the agent's thoughts are material. So therefore there is no meaningful distinction between efficient cause and material cause, but the Kalam needs that, because if everything only has a material cause, then the Kalam's going to fail. Another assumption is you're going to have universal causation, so everything that begins to exist as a cause, but you also have to have free will. And I'm not saying you can't have both of these things, but they're certainly problematic. I mean, if my thoughts have causes, my thoughts certainly begin to exist. If they have causes, in what sense am I free? I mean, it's going to be difficult to marry those things together. I'm not saying it can't be done, but it's certainly, you're in a bit of a mess philosophically, and certainly there's no consensus on these things. It's not like, oh, yeah. Well, philosophers all agreed about this stuff. They certainly aren't. You're also going to need a causal interpretation of quantum mechanics, because if quantum mechanics does allow for a breakdown of causality, that could be the candidate for the beginning of the universe. And there's no consensus that the quantum mechanics is causal. Clearly, I think the consensus is actually the other way around. But certainly there's no consensus on these matters. And again, it's a mess. It also seems that laws of physics are not causal. So if we imagine that we could have a simultaneous cause in that sort of sense, well, again, this Lorentzian model kind of, in some sense, it's very difficult to talk about causality of these sorts of things. But if you think you could meaningfully talk about this sort of simultaneous causation, maybe the laws could be the cause, and they exist necessarily. Now, a lot of people will say, no, laws are just descriptions. but we don't know that to be true. Other philosophers of science say no, laws are more than descriptions, and that's what somebody Vilenkin's model needs. And maybe he's right. Who knows? So just to conclude, I think we just don't know if the universe began to exist. And even if it did begin to exist, we don't know if causation is meaningful. And there's certainly problems with saying there could be causes when there's no space-time, no arrow of time, no laws of physics. And I think even if the universe does have a cause, we don't have any convincing reason to think that it's an omnipotent God. Obviously, that gets into, ontological arguments, stuff like that, which is a separate issue. So to me, to sum up, I think the Kalam argument is not that we know the assumptions are false, but we just don't know them to be true. And therefore, you can't trust the conclusion. And that's it.
Thank you. Do you want to unshare your screen at this point?
Yep. Okay. Hang on. Stop share. It's very difficult to see the cursor on this thing. There we go. Stop share. Okay. There we go. Okay, right.
Folks, if anyone wants to ask any questions before we finish for today, then there's the time to raise your hand or submit a question. We have a hand raised from, actually we have 2 hands raised. We'll go for the first one, Vladimir, specifically from Montenegro. Vladimir, are you with us?
I'm here.
All right, you're here. Great. Go ahead.
So I unfortunately missed the first part of your presentation, which involved various physical theories about whether the universe does or doesn't have a cause. But I wouldn't really be qualified to address that anyway. My main concern is the second part of your argumentation, namely the philosophical part of the argumentation. And you've outlined several objections to the Kalam in that manner. Yeah. So you firstly say that Kalam assumes the A theory of time to be true.
No, I didn't say that. I said the philosophical defense of the Kalam. The argument that there can't be infinite. I think you could still build a Kalam on the physics, but not on the philosophy. I think the philosophy.
Well, yeah, but it wouldn't be the Kalam that we are talking about in the sense of the one that Craig defends, the one we referred to, right? So the standard formulation of the Kalam argument would fail if the A theory of time was not true. We agree on that. Now, the issue with that, I find, is that the A theory of time, and this is why I asked the question previously as to how you would define time, because it seems to me in all of your argumentation, it has to be assumed that the B theory of time is true. And you obviously went on with that, with how you addressed the arguments against the infinity of actual infinity and stuff like that. And I think there are fundamental problems with the B theory of time and with interpreting the world as being in sort of a B theory of time. So if the B theory of time is true, there is no causality. Everything is in a time-space block, and time is simply a line going through that block, right? But the issue with that is I don't see how there could be in that static block any sort of an illusion of movement, because obviously we are talking at the moment, it does seem to us that the time is passing, yet the B theorist has to maintain that the block itself is static, but at the same time he has to maintain that there is an illusion of passing of time within the static block for the agents within the block. I think that's quite a problematic proposition.
Okay, sorry.
Yes, furthermore, I think the theory would create a problem with the second, with the law of non-contradiction, because you would have, under endurantism and perdurantism, you would have agents or objects enduring through time, right, as either spatial or in-time objects. And the problem with that would be that you would have, for example, objects alive, like humans alive at one time and dead at another, and they would be alive and dead at the same time because there is no time in the sense of an A theory. So I think there would be problems in that manner. How would you address that?
Okay, so I think there's this, as I understand it, it's just not true that there's no time under the B theory. There is time, and that people experience a passage of time. It's not that there's no time. It's just that you can't agree on the passage of time. Let me give an analogy here. Would you agree that you can say where you are, with your location, right?
Yes, I completely understand your objection in that time.
Let's just, for the listeners, we'll try and unpack it. Okay, all right. So you have your location, I have my location. I can say I am here, but there's no universal here, right? If I move, if I go to another location, for me here is different, okay? Similarly, you have up and down, right? Where I am sitting, I know what's up and what's down, but there isn't a universal up and down. I experience up and down because I'm sitting on a planet, right? If I wasn't on a planet, I wouldn't have an up. So it's not that there's no time under the B theory. There's still time and there's still passage of time, but there isn't a universal time that everyone can agree on this is now. So it's just, there is time, there is causality, but there isn't a universal agreed upon now.
Oh, I understand fully your objection and your view on this. My problem is how this works under the B theory. I understand what the B theory says on the issue. My problem is that if it is the case that we live in a static time-space block, that time is simply, you could say, a spatial dimension going through the block with points being objects on that line. You simply can't have an illusion. Those objects can't have an illusion of passage of time if the block itself is static. So if it is objectively true that time is a spatial dimension, there is no movement within that spatial dimension.
Well, but it's not true. Time is not a spatial dimension. Time and space can be translated from one to another, but they're still different things, right? It's not that time right. It's like a currency. You know, you can exchange pounds for dollars, but pounds and dollars are still different things. So that's the exchange rate. So what you have space time. That's, you know, you have, people can agree on space time, but they can't agree on what's space and what is time. So it's the space time that is the block. It's not time that's the block. I think that's a misunderstanding.
I said that.
Okay, well, let me, and it's not just me that says it. I mean, this is complete consensus in the physics community, and even in the philosophical community. The only survey I know that's ever been done on this, the B theory was twice as popular as the A theory. So the A theory is, now that doesn't prove anything. I agree with the reasons, the discussions that we'll have, but all I'm trying to say is the Kalam is not without difficult assumptions, and there are assumptions that are, I would say, mostly rejected by physicists and not really. It's not like the philosophers are on the other side. They're not, you know.
Yes, I fully understand the series of explanations and objections on the B, as I previously said, and I didn't say it's a purely timed block. It's a time-space block. Again, the issue I find within this block is that if it were the case that reality is in a time-space block, we wouldn't be experiencing the reality the way we are, because there's obviously movement, and even though it may be relative, there is movement within this block. But if this block is truly static, if there is no objective time going through it, then there doesn't seem to appear a way in which this could be the case. But I guess we got kind of hung up on this. There are some other issues I wanted to address. You stated that in terms of causality, right, there couldn't be a simultaneous causation. You addressed the Kant's attempt to say that there is a ball on a pillow, and you said that it's impossible because there are some problems about the speed of light, and they may appear to be instantaneously caused. But
I didn't say simultaneous was impossible. I just said that it's problematic, shall we say?
Yeah, it's problematic. But
given, I don't think are examples of simultaneous causation, and my understanding of causation is that causes are prior to their effects. Now, maybe you could have simultaneous causation, but it's not something that we know about. There's something that's just a consensus on. And yeah, of course, things are simultaneous, which is what you'll often hear some philosophers say. And I just don't think that's correct.
Yeah, I think the reason the proponents of the Kalam argument use it is not to say that within our time and space, there could be objects simultaneously causing one another in some, or effects simultaneously causing one another.
They do say that. They do.
Well, the point is they use analogies for that, but the issue we're dealing with is the very beginning of the universe. If we assume there is God and that God is creating something, then at that point there are no laws of physics, right? it could be the case that something is caused in the manner in which these analogies describe it. Now, of course, these analogies are imperfect. I absolutely agree with that. But there doesn't seem to be a logical impossibility in terms of this causation, which is all we need. If it's logically possible.
I'm not saying. Well, I'm saying that what we know about causality and what we understand and what we experience and so on and so forth, and as we understand the laws of physics, causes precede their effects.
I agree.
Now, could you say that there's some cause that's simultaneous? Maybe you can, but then you're appealing to something that we're not really familiar with, shall we say, and is certainly problematic, raises difficult issues. Like, how would you be able to say which one is the cause and which one is the effect if they both are simultaneous? I just can't see how you could say one is the cause and one is the effect. When we use the Hill criteria, we say which is cause and what's effect. Well, the one that happened before has to be the cause, right? So how would you say which one is the cause and which is the effect if they're simultaneous with each other?
Well, I mean, it could be the case that when again, I'm assuming the theory of time, but when God is willing, we think that God is atemporally existent before the universe, right? Meaning that he wasn't in time. This omniscient being was, just self-existing at that point. And then he decided, again, he is omniscient, atemporal. There was a decision of creation. And at that moment of decision, there was Big Bang. The universe popped into existence ex nihilo. So in that sense, there is a simultaneity between God's desire for the universe to be created, the beginning of time in an a-theory sense, and the creation of the universe. That's the way we describe it as.
Well, of course, you can say those words, but how would you determine whether it was the universe coming into existence causing God to exist and not God causing the universe to exist?
Well, because we assume that God is a necessary being.
Right. But then you're making that assumption, right?
I agree. I agree.
So what I'm saying is that the Kalam has these difficult assumptions, right? It's not something that it's presented as you just know it intuitively. Everything has a cause, right? And what I'm saying is, no, you have to assume some cause that we have no knowledge of, right? And so it's not based off our intuitions and our experience of the world. That's a false
here's the thing. When it comes to God creating the universe, right, we obviously have to make certain assumptions about, say, God being possible, right, an omnial being possible and things like that. Of course, there are assumptions. But when you're speaking of causation itself, regardless of the universe, balls, and whatever else there is that's being caused, we are speaking of an intuition. So in some possible worlds, it is possible that the universe pops in uncreated, out of nothing. Yet that's logically possible. The question we ask is whether it's metaphysically possible, whether there is a mechanism by which such could be done. And there doesn't appear to be a mechanism by which such could be done. You mentioned an example previously, there could be no laws if there is nothing that limit the universe from popping into existence, right? And I agree, but there's nothing else that would enable the universe to come into existence at that point. So it's not, we have to base it off of our intuitions that creation out of nothing without
one thing I want to say is that the lesson of physics in the last 100 years or so is that our intuitions are very poor guides for what happens at a fundamental level. So it's our intuition that time is the same for everyone, and relativity says no. It's our intuition that you can't have superposition, but quantum mechanics says no. It's my intuition is that the Earth is flat and the sun goes around the Earth. I mean, I only know intuitively that seems the case. You can't see the curvature of the Earth.
There's a difference between observational intuition and metaphysical intuition in these terms. For example,
your metaphysical intuition, I would say, to me, it's intuitive that everyone should measure the speed of light different, depending on their speed, right? That is a metaphysical intuition that I have, that speeds should be subtractive, okay? But it turns out that it's wrong, right? Turns out.
Where did you get the idea of the speed of light from? That's not a basic intuition.
No. It's not the speed of light that's the basic intuition. It's basic addition. That's
yeah, but you have to have the idea of the speed of light in your mind for that to happen.
No. Wait. Let me make this point. Okay. If I travel at a speed, let's say 100 kilometers an hour, and you travel at a speed of 100 kilometers an hour, what would you intuitively say I should see your speed as?
Depends.
No, it doesn't. What does it depend on?
Well, I mean, if you're driving in a car next to me, it seems to that both of us aren't moving, you know?
Right. So I should observe you as not moving. Agreed?
Well, yeah, if you're just looking at me and not the road. Yeah, sure.
Right. Okay. Right. Now, what if you put your foot on the accelerator and go 200 kilometers an hour? What should I see as your speed?
Well, you would speed right past me, and I guess I would be double as fast as you are.
So what should be the speed that I observe you to be at?
Well, 100 kilometers faster than you are, perhaps.
Yes, exactly. It's not difficult. It's not trying to trick you here.
But I don't see how this helps.
So hang on here. I'll get to the point, right? So if you go 300, you should see it as 200. You don't have to know anything about cars for this. This is just basic intuition, right?
No, it's observation.
About the physical world for this, right? If some object goes past me at some speed, I should basically subtract my speed and their speed and get the speed that I observe them, right? That's a basic intuition. It turns out...
No, that's observation and calculation.
No, you don't have to make... I don't have to have seen a car do this, right? I can just deduce this, right?
Yeah, you can, but that
right.
It's not.
No, but it's not
still based on
correct.
you.
It's not correct. For the speed of light, well, no matter what speed the speed of light goes at, I will measure it. No, if I see a light beam going past me and it goes at 300,000 kilometers a second, and I'm going at 200,000 kilometers a second, right? What should I say the speed of light is?
Well, I mean, it would be 100,000 kilometers a second difference, right?
Right. But it's not. That's wrong. You're absolutely wrong about that. It turns out the world doesn't work that way.
I'm agreeing with you.
Right? So it turns out that the speed of light is the same. If I go 200,000 kilometers a second, I still measure the speed of light as 300,000 kilometers a second. Now, the point I'm trying to make is that when it comes to fundamental physics, we've learnt that our intuitions are not good guides.
I'm agreeing with you.
Okay.
But when I speak of metaphysical intuitions in terms of what seems to be possible, it's quite possible for me to state that, yeah, you know, if I'm moving in parallel with you in a car and you speed past me and we're both moving at some speed, then, you know, speed might be relative in that sense. I agree with you. This is very obvious. When we speak of metaphysical intuitions, like, say, things not coming out of absolute nothing, what we're saying is that there couldn't be a metaphysical way in which this happens. We're not basing this on our feeble observation of the world that could be in some way wrong, right? When we're sitting here and seeing the sun go across the sky and we say, oh, you know, it could be that it's just circling up above the earth, right?
Why should I trust your metaphysical? Why should I trust your metaphysical intuitions about nothing?
Well, because they seem to be correct. See, when Alvin Plantinga...
How do they seem to be correct?
Well, they seem to be correct because they're intuitions. That's the definition of an intuition. When you read, for example, when you read Alvin Plantinga and his books on justification of a belief, and this has to do with an idea of properly basic belief in Reformed epistemology. It is the case that we have certain properly basic beliefs. For example, a properly basic belief of ours is that we are not brains in a jar stimulated by electrodes. Our idea is that we are in a real physical world. Or that, for example, it is not the truth that solipsism is the case. We believe that there are other minds. These are some very basic intuitions of ours. And unless it is the case that they can be proven wrong, necessarily proven wrong, we are justified in believing them. Now, we are perhaps not warranted in believing that. We may not have any evidence externally to support them, but it is the case that they are justified beliefs. And that's the point. If we do not have any very, very powerful overturning evidence to state that it is the case that something can come out of metaphysical nothing, or philosophical nothing, then it is the case that we should state, okay, perhaps something cannot come out of nothing in that manner without an efficient or material cause. So that's the whole point of what I'm stating.
Okay, so let me respond to that. So first off, you said you missed the scientific presentation that I gave. Okay.
Well, I mean, I could address certain things about it, but I missed it for the most part.
Okay, all right. So the first thing to say is that I'm not actually arguing that something can come from nothing. Okay, in fact,
I understand it.
Okay,
you're laying out possibilities.
Okay, fine. That's fine. That's fine. Just one issue at a time. So first off, I'm not arguing that something can come from nothing, right? Secondly, what I said was that. So another thing that I pointed out was there is a model which is the closest to something coming from nothing, which is the Vilenkin tunneling from nothing model. And here it's the case, you could argue that it's not really from nothing, it's from the laws of physics. And so maybe the laws of physics is in that sense, this, cause in that sense, if you want to go down that route. Thirdly, I just don't agree with your intuition. To me, my intuition tells me if there was nothing, maybe something could happen because there's nothing to prevent it from happening. We have things, your intuition says something can't come from nothing because there's nothing to cause it to happen. My intuition says, well, there's nothing to prevent it from happening. I don't know that my intuition is right. I have no idea. And I think you have no idea. And we have different intuitions about this. And we have no way to distinguish which intuition is correct. And
well, I would say you are justified in your intuition. If there is no evidence against it, I would say you are justified.
There's no evidence either way, is there? We've never seen that.
Yeah.
I think we're going to we'll move on to the next caller because we do have a couple other.
Thank you, Vladimir. Thank you,
Vladimir, for calling. All right, so let's go to David. David, are you there? Maybe not.
Maybe he could type his question.
Yeah. In the meantime, just a couple of questions in the Q&A box. An anonymous attendee says, when you mention causal interpretations of quantum mechanics, are you arguing deterministic models or synonymous with causal ones? Because it's common in philosophy of science to see indeterminism and causality as perfectly compatible.
So, yeah, I guess I'm saying that indeterminism does undermine causality. That's my view. Yeah.
Another attendee says, I don't think rejecting the laws of nature as descriptive helps the atheist. The main school of thought would be Platonic, but a common difficulty is why some laws and not others. Laws on this idea would not be fundamental.
Okay, so that's a very good question. Right, so to me, this is only really, we're talking about not whether laws of physics are descriptions or more than descriptions, is really just we're talking about the Vilenkin tunneling from nothing model. So I'd be happy to say, yep, laws of physics are perfectly descriptive. Then I think the Vilenkin model would be a difficult one to sustain. But the atheist doesn't need the Vilenkin model. They can happily go to, plenty of other models, the CCC model, the bouncing model. I mean, the atheist doesn't need the Vilenkin tunneling from nothing model. I know Lawrence Krauss probably creates the impression that the atheist needs this, but I just think that's wrong, and so to me, no big deal. Now, if Vilenkin is correct, then the laws are obviously more than just descriptions, and then the Vilenkin model can work. And I don't see how the atheist would have a problem with that model. It's perfectly fine for the atheist to say, "Yep, his model's right, and that's how the universe came into being, and that's our that's where our chain of explanation bottoms out at the laws of physics, and that's that." Now, are they necessary? Are the laws necessary, or could they have been different? I mean, I think we have no way to know that at the moment. I mean, maybe someone clever will come up with a way of understanding that. I've interviewed some physicists, like Roger Penrose, for example. He thinks that the laws couldn't have been anything different to what they are. And not only the laws, but the constants too. I mean, they think these things are necessary. A lot, in fact, in that conformal cyclic cosmology film, a lot of the people that work on that model, they, you know, because inflation gives you a multiverse and that will give you many different types of universes. They think in CCC, no, probably not. I mean, they do entertain the constants could be different between the different cycles, but generally they're not overly keen on that. And they were like, no, we think, I'd bet on that it's all necessary, that the laws have to be what they are and the constants have to be what they are. Of course, I just don't think we know. I mean, who knows? Could be either.
If parameters have to be the way they are out of physical necessity, does that not then shift the fine-tuning problem back a step? Because then it would be a remarkable coincidence. It just so happens to be that the laws of nature have to be the way they are, such as are conducive to produce life. Would that not just shift the problem back a step?
Well, it wouldn't be a fine-tuning problem in the way that it's presented. Let's put it that way. So the way it's normally presented is that fine-tuning means the probability is small compared to some range. Okay, so I can imagine the constants being here, 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 you know, and only here. So you could draw out a plot, you know, and only in this small space of the plot is life possible, right? So your question is, well, why are we here? You know, why not over here? So if the laws of physics are necessary, and if the constants are necessary, they have to be what they are, then, well, I mean, think of the dice roll video that Justin Briley produced, right? You know, how is it that it's 6 every time? You know, well, if every side of the dice is 6, should you really be surprised? Is it an amazing coincidence that every time you roll the dice it's 6? And you might say, well, but still you need to explain why are the laws conducive for life? But okay, fine. I agree. You still want to understand that, but it's no longer the fine-tuning problem of the probability the way it's presented, because you can't say, well, I can imagine these laws and these laws and these laws, because there's not some sort of number of different laws that you have. So you can't make it a sort of numerical problem. I agree that you still have to ask the question, well, why are the laws conducive to life? But it's not the fine-tuning problem of the way it's presented, at least.
Sure. I mean, it would seem to me that if there was some kind of governing underlying principle or theory of everything or something which explained why the laws just have to be the way they are and they couldn't be any other way, and that set of constants and parameters just so happen to be that which is conducive to life, that would then still be a fine-tuning problem, just back a level from what it was previously.
To me, it's a problem, but it's not a fine-tuning problem, because the whole way that people understand fine-tuning is there's some range of possibilities. There's a very large range of possibilities, and we got the right one out of the large range of possibilities. But if they're necessary, there isn't a large range of possibilities. So it's not, you can't call it fine-tuning anymore. You could still call it a problem. I'm not saying there's nothing left to be explained, but it's not, I mean, I guess it's a separate.
Well, whatever you want to call it, it's still suggestive of design, I think. But
well, to me, I mean, David Albert said, well, then you could ask, why is it, you know, F equals MA and not if F equals half MA, you know?
Yeah.
Like, it's just like, well, that's what came out, you know? You think life is important because you're alive, but why should someone with a God's eye view think it's important? You know, so what?
Yeah, I mean, I would turn to formulate the argument in Bayesian terms. So I would say that, well, what's the probability of this sort of life, you know, complex, conscious, you know, sentient life existing on the hypothesis of theism, and what's the probability of life existing, as we know it, you know, sentient life on the hypothesis of atheism? And obviously, it's got to be much higher on theism than it is on atheism, and so it's evidence for theism over atheism.
Why is it higher under theism?
Because of the improbabilities against it.
But what? Okay, so let's put it this way: all we know that the life exists, right? But there's no argument from theism that just because life exists, right? So what you're trying to argue is the probability of life is low, right?
Right.
It's not that life exists. We know that life exists. We can only observe life.
Right. Sure.
Right. So it's that the probability of life is low. Yeah. So really the question should not be what's the probability of life given theism or atheism. Should the probability of life be high or low? Right. Under the different assumptions. So I could just argue Well, if I'm a theist and I think God loves life, who sets the probability for life? Like when I make a dice, I'm setting the probability because I make the dice. So I could make it so that 6 is guaranteed by painting 6 on every side. Or I can make it 6 is unlikely by painting 6 on only one side, right? Because I'm making the dice. So with the universe, who sets the probability?
Oh, God does.
Right. So if I think that God is life-loving and he wants the universe with life, I should expect him to set the probability for life to be high, shouldn't I?
Right.
So the fact that all the fine-tuning is telling us, if it's right, and by the way, many of the physicists that we interview say we don't think the universe is fine-tuned, but
it is the majority position among.
Is it? I've never seen a survey been done.
I could give you quotes from people who say who are knowledgeable in the field.
Craig gave a list of people and who I've interviewed, and he said they say that the universe is fine-tuned for life, and I've asked them, and they say no, I don't think it is.
Okay, well, I mean, I could dig out some papers which say that it is the mainstream view.
Let's just assume that it is, right? Okay. All I'm saying is there's more dispute about that than is painted by theists, right? I'm not saying it's not true. So let's just grant that it's true. So what you're saying is that the probability for life is extremely low, right? Now, but you just told me that if given God, you should expect the probability for life to be really high. So haven't you just disconfirmed the God hypothesis?
Well, no, because
expected it to be high and it's low.
God sets the laws and constants and parameters to their values that we find them at in our universe, which is conducive to life. So and so by setting those constants to their respective values, then the universe is conducive to sentient life.
But take a step back, because we know that life exists. That wasn't the surprise of fine-tuning, right? Fine-tuning wasn't the discovery that life exists. Fine-tuning is supposed to be the discovery that life is improbable, right? So can you deduce that God exists from the fact that life is improbable? To me, you told me that you expected the probabilities to be high. That life should be probable.
No, well, it's not that it's probable, it's that it's more probable on the hypothesis of theism than on atheism.
Well, again, the probabilities, if the probabilities are set by God, then we should expect them to be high, I think, right? And so all we found is that the probabilities are low. Now, that's not, I don't see why that's low under atheism, because, so under atheism, you've got a number of possibilities, right? It could be that the probabilities are just wrong, that it's not improbable. That would be the necessity argument, right? Or not just necessity. Some physicists say it's just wrong to say the universe is fine-tuned, right? That's another possibility. Another possibility is a multiverse, right? In which case it's only low under atheism if the constants are generated randomly, and we're right about fine-tuning, and there's only one roll of the dice, right? Atheism doesn't say any of those things. Atheism doesn't say the constants were generated randomly. Atheism doesn't say there's only one roll of the dice. And atheism doesn't say that the things are fine-tuned, right? Any one of those is perfectly, we could accept fine-tuning and say there's a multiverse, or we could say it's necessity, or, there's plenty of, you can't say it's low under atheism. It's only low under atheism given those other things.
Okay, I just want to, David, I think I saw David just a minute ago. He has a physics background, so he'd be quite interesting to talk to. Are you there, David?
Yes.
David,
you are.
Ask a question. I really want to hear what his question is. Can he email it to you or something?
I can hear him very faintly. Are you there, David?
Yeah. Can you hear me better now?
I can hear it. Hear it. Just about.
Yeah, go ahead.
Okay. Yeah. So I put my argument in chat. So yeah, I find I copied down the list of assumptions of Kalam, and I find most of them to be very similar to situation that a character in a story would see if he looked at the story of how the author wrote the story that he's in. And so and I'm not familiar with A and B theories of time, but B theory being where basically all of space-time is laid out, and our experience is constituted by the moving forward through that block. Sounds very much like the process of reading a story that an author has already written, and experiencing what the characters experience. And in the
David, can you speak up? We're really struggling here. Could you shout? Maybe try and make the question a bit briefer and shout it as loud as you can.
Jonathan, would you like to read my what I posted in the webinar chat?
Yeah, you can post it in the chat. Yeah, right, Jonathan?
Okay, so you said, I find most, if not all, listed assumptions of Kalam to be similar to the situation in which an author writes a story with the way the author causes the story to exist, and progress being different from the way in which the characters cause things to happen in their parts of the plot. The author is sovereign over the plot, including what the characters with free will do. He can cast the story of a world where things follow more narrow rules than he experiences. He is outside the dimension of time that the story is inside, and can thus say, it felt like 1,000 years when I wrote this one. Second segment of the plot. But I can flash the whole plot through my mind in 1 second. That's what he said.
Okay, I'm not quite sure what the question is, but I'll try and sort of address it. I don't think there could be an analogy there because you come up with a story before you write it down, right? And also the characters, you said, have free will, even though the story is the storyteller is sovereign over the story. I mean, to me, those two things are in conflict. Like the characters of a book, Harry Potter doesn't have free will to do something different to what J.K. Rowling says he's going to do. So it's not a free agent, So I'm not really quite sure what the question is, but I just don't think the storyteller analogy is useful for the universe. Yeah, I'm not seeing the analogy there. Sorry, maybe there's a clearer way to put the question.
Okay, I think maybe we'll wrap up at that point. It's 10:15 here.
Okay, sounds good.
Right, thank you so much.
Before I finish, that I just want to attribute the argument I just made about fine-tuning is not my argument. It comes from a Christian philosopher of physics.
Which one?
Princeton, Hans Halvorson.
Okay.
And he made this argument. He thinks fine-tuning is a very bad argument for God. And he thinks it disconfirms theism.
Well, you said he's a Christian, and he says this.
Is, but he thinks that you can't say the universe is fine-tuned.
Okay, but you said he thinks it disconfirms theism. You said
yes, or Christian theism.
But he's a Christian.
Yes, because he doesn't accept that the universe is fine-tuned.
Oh, I see.
Right.
I see.
So, but if it was, it would be a problem for theism.
Right. Okay. Can you send me that paper, because I would very much like to have a look.
Yeah, but he gave a talk. So if you just go on YouTube and type in Hans Halvorson, you'll see his talk.
Okay.
Yeah. Cool. All right. Well, look, thank you very much. I appreciate it. It's been a pleasure.
Finally, just before you go, do you have any recommended resources where we could read more on this stuff?
Absolutely. You should go on my channel, SkyDive, and we've got a series called Before the Big Bang, and we've got up to episode 7 now, and we've got another 4 that are in the works that will come out in the next 12 months. So that's where you should start. But no, more seriously, for a more neutral place to go would be, well, first off, Alan Guth's book, The Inflationary Universe, is very good. On Carlo Rovelli, he has a great book called, he's one of the founders of Loop Quantum Gravity. He's got a great new book out, which I have right here, hang on, called Reality is Not What It Seems.
Okay.
Really excellent. It's quite short. He's a big best-selling author. His book, 7 Lessons in Physics, outsold 50 Shades of Grey in
Oh, wow.
in some countries, or at least in his home country of Italy. It was a huge bestseller. That's a very good book. And there's a very good essay, very short, it's on Einstein Online, which is, I think, a page set up by the Max Planck Institute for Gravitational Physics. And they've got a really good essay called, which kind of sums up what I'm saying.
Okay.
And it's called A Tale of Two Big Bangs. And what they argue is kind of what I'm arguing, is that when we say Big Bang, we don't really mean the universe had a beginning.
Okay.
And one last thing I think everyone should watch, probably your listeners have all watched it, is the debate between Sean Carroll and William Lane Craig. I think that spells out a lot of the issues very, very well. It's a very good debate. Both sides very, very good at painting this debate.
Okay, good. Yeah.
All right. Thanks very much.
Thank you.
Bye-bye.